reference paper in one Petro presented at the Middle East Oil and Gas Show and Conference, MEOS 2021, where she was the only female undergraduate to be presenting. Finally, Mariam is interested in the application of machine learning in the energy industry. And now, Engineer Mariam, you can start.
Thank you, Karim, for this introduction, and thank you, SP Al-Azhar, for this invitation. I'm really happy to be here. So today, our webinar will be about applying machine learning in the oil and gas industry. So we'll be going over Okay, I think I was muted. Okay, so thank you, Karim, for this introduction. Thank you, SP Al-Azhar, for this invitation. I'm really happy to be here. So today we'll be going over the following: an introduction about machine learning, artificial intelligence and data science, the basic types of machine learning models, and examples of the applications of machine learning in petroleum engineering, and an example on how can we determine the natural gas density using machine learning algorithms, mainly the artificial neural networks. And of course, we'll be having some time at the end for your questions. So let's start. As you all know, digital transformation, machine learning, data science, and AI, they all have become buzzwords in the oil and gas industry with numerous applications that can guide us into better decisions with smart actions. But what's the difference between AI, machine learning, and data science? So AI is a system or a machine that is trying to mimic the human behavior. It covers machine learning, natural language processing, and robotics. So machine learning is a subfield of AI, where we are using an algorithms that use past and current information in a data set in order to determine hidden trends to come up with a predictive model that can be generalized for future applications. And we have the deep learning, which is a machine learning algorithm or technique that is inspired by the human's network of neurons. Now, AI, machine learning, deep learning, and data science, they are interconnected. Why? Because when we talk about data science, we're using statistical methods and mathematical methods, along with AI and machine learning algorithms to analyze data or big data in order to come up with predictions. But of course, data science is not limited to statistical methods and machine learning algorithms. It covers the whole spectrum of data processing. So data science is important for machine learning because as the definition states, in machine learning, we are trying to generalize knowledge from the data we have. So machine learning models, they are as good as the data it is given. If we don't have a good, well-processed data, we can do very little with machine learning models. So machine learning models, they are as good as the data it is given. So we have three basic types of machine learning models. We have the supervised, the unsupervised, and the reinforcement learning. In the supervised learning, we are using a training set to teach the model to classify or predict outcomes accurately. It's further subdivided into two main groups. We have classification and regression. For classification, we are assigning data points to a certain category. And for regression, we are trying to understand relations between dependent and independent variables. Second, we have the unsupervised learning, where we are trying to find trends in hidden trends in unlabeled data. And we have clustering and dimensionality reduction. In clustering, we are grouping points or data together that have similar properties or features. And for the dimensionality reduction, we are reducing the dimensionality of the data set. And this is very important when we are dealing with high dimensional data. And I want to highlight here that although the dimensionality reduction is considered an unsupervised learning technique, it can be used as a pre-processing step to reduce the dimensionality of the data set before working with supervised learning techniques, algorithms. And finally, we have the reinforcement learning. In the reinforcement learning, we are training or teaching the model through trial and error, and then establishing a certain reward for the best outcome. So comparing the supervised learning with the unsupervised learning, in the supervised models, the input data is labeled. We are using a training data set, and the data is being classified based on a training set. On the other hand, for the unsupervised learning, the input data is unlabeled. We're using just input data set, and the unsupervised algorithms, they use properties of a given data in order to classify it. Generally, the supervised algorithms, they are used for prediction purposes, while the unsupervised algorithms, they are used for analysis. Now, for classification, we are trying to predict categorical variables, so the output values, they are discrete. For example, if we are trying to predict lithology, so the output is discrete, so it's either, for example, permeable sandstone or limestone. For regression, we are predicting numeric variables, and the output values, they are continuous. For example, if we are forecasting permeability or porosity values. And for clustering, we are identifying a pattern or a group of patterns that have similar objects, or of similar objects that have similar properties and features. And finally, the dimensionality reduction, as we can see, we are reducing the dimensionality of the multi-dimensional input data, where we are removing some input parameters from the data set. So machine learning, or we have several applications for machine learning techniques in the petroleum industry, which can solve and optimize various problems, which can result in an increase in profit and efficiency and reduction in cost. So here are 6 main areas where we can apply or get the help of machine learning to help optimize operations in the oil and gas industry. So first, for anomaly detection, so to know whether the operations are normal or not. Second, for a prediction, so to know what will be the value of a certain parameter, or what will be the operational condition in the future. And for a diagnosis, so to what category does this pattern, a certain pattern, belongs to? And to know if we can replace certain laboratory experiments by computational methods, because as we all know, the laboratory experiments, they are time consuming and they are somehow expensive. And we can, with the help of machine learning, advance the process control. So to know how shall we change a set of points in order to keep the operations stable. And finally, for process optimization. So here are some applications of machine learning in reservoir and production engineering. So we can use ML algorithms to forecast the pressure, volume, temperature properties. So PVT properties, they are important for material balance calculations, and they directly impact the reservoir performance and evaluation. We can also forecast the rock properties such as the porosity and permeability, which are important for the reservoir simulation. And we can forecast asphaltium precipitation, wax deposition, and optimize enhanced oil recovery techniques. For example, we can accurately get the values of the interfacial tension and the minimum miscibility pressure. So the minimum miscibility pressure is an important parameter when we are applying gas injection. So several research has been conducted to unfold the potential applications of machine learning. For example, Khamis and Fatah, they utilized the artificial neural network and the support vector machine, the functional network, in order to predict the gas-oil ratio, and they used the pressure, temperature, the bubble point, the condensate yield, the oil and gas density at stock tank conditions in order to predict the GOR. And the average absolute percentage error for the model was 0.12, which indicates an acceptable accuracy for the model. Ramirez et al. Utilized ANN to predict the bubble point pressure, the oil formation volume factor, taking the temperature, the GOR, the relative gas density, and the API as input parameters. Another study used machine learning algorithms to forecast oil viscosity. We can also use ANN to predict the performance of the water alternating gas using CO2. And the input variables in this case would be the water alternating gas ratio, the duration of each cycle, and vertical to horizontal permeability ratio, and the initial water saturation. Also, machine learning can be applied in drilling engineering to decrease the drilling cost and improve the drilling operations. So we can predict the mud density, the loss circulation, the mud cake permeability, the filtration loss, and the settling velocity of cuttings. So Ahmadi et al., he used the least square, or they used the least square support vector machine in order to estimate the loss circulation volume using the mud weight, the mud flow rate, the depth, and the pump pressure as input parameters for the model. And the coefficient of determination was 0.999, so revealing a quite good accuracy for the model to predict the loss circulation. Another study used the random forest, the convolutional neural network, and the hybrid convolutional neural network and the recurrent neural network in order to classify the rotate drilling and the slide drilling. And we can use the random forest to predict the rate of penetration. Also, machine learning can be applied in to improve the reservoir evaluation and in the exploration phase. So we can use the least square support vector machine to estimate the shear wave velocity, and we can use the random forest decision tree, the support vector machine, to predict the total organic carbon. So now we'll be going over a specific example, which is how to determine the natural gas density using machine learning algorithms, mainly the artificial neural networks. This research was published at Petro, which during my undergraduate studies last year. So by the SPA, the Society of Petroleum Engineers. So natural gas density is considered an important metric that influences the computation of various variables that are needed in order to analyze the gas systems. So these variables, they include the gas reserves, the gas pressure gradient, the gas compressibility factor, and the gas flow rate. Earlier, we used to rely on laboratory experiments in order to get this value for the natural gas density. But the laboratory experiments, they are time consuming and they are costly. Later, we relied on empirical correlations and models. However, these correlations, they have a certain degree of inaccuracy, and their application is limited to a certain set of operating conditions. So of course, they don't provide results as accurate as the laboratory experiments. So we need to find a way to accurately calculate natural gas density, and we can do so with the help of machine learning. So the main objective here is to employ ANN to forecast the gas density based on three main influencing variables, which are the pseudo-reduced pressure, the pseudo-reduced temperature, and the molecular weight. And we compared the ANN model with another model, which is the ANFIS, or the Adaptive Neurofuzzy Inference System. ANN is a machine learning algorithm that mimics the human biological neuron. So this algorithm is able to relate inputs to outputs. On the other hand, the ANFIS, it integrates the learning ability of ANN and the reasoning ability of the fuzzy logic systems. The fuzzy logic systems, they are algorithms that imitates the human's reasoning and cognition. So the data set was made up of 4,500 data points representing the three influencing parameters. So the pseudo-reduced pressure is equal to pressure of over the pseudo-critical pressure, similarly the pseudo-critical temperature. And the data set was divided into 70 to 30% ratio. So 70% of the data was used for testing, for training the model, and 30% was used for testing. We converted the output parameter, which is gas density, to log gas density to train and test the data. Why we did so? Simply to improve the correlation and improve the results, the training process. And the output was converted back to real values, to real gas density values. So as we can see, we have a negative correlation between the pseudo-critical temperature and the output variable, which is the log gas density. And we had a positive correlation between the molecular weight and the output variable. Similarly, we have a positive correlation between the pseudo-reduced pressure and the output variable. For the data analysis, we calculated the mean, the max, the minimum, the maximum, the average, the standard deviation, the skewness, and the kurtosis. Just as a reminder, the skewness is the measure of symmetry, or more accurately, the lack of symmetry. For the kurtosis, we're measuring how heavily tailed or how light tailed the data is with respect to a normal distribution. So the minimum value in our data set for the gas density was 0.004 gram per centimeter cube. The maximum was 0.753, and the average was 0.261. The standard deviation was 0.196. So the data is clustered near the mean. And the skewness was 0.594. So the data is slightly skewed. And the kurtosis was minus 0.593. So the data set is close to a normal distribution, we can say. So we applied the ANN and the ANFIS to train and test the model. We used 3 main error metrics to compare the 2 models and then acquire an ultimate model. So first we used the average absolute percentage error. So which is 100 over n, the number of data points, times the summation of the actual minus the estimated value over the actual value in absolute. So for the AAPE, any value less than 5% indicates that the model has high accuracy, gives high accuracy for predicting the data set. Any value between generally between 10 and 25% shows a moderate accuracy. However, any value more than 25% shows a very low accuracy for the model to predict the data. And second, we have the coefficient of determination, which is 1 minus the summation of the actual value minus the estimated value squared over the actual value minus the average actual value squared. For the coefficient of determination, any value close to 1 shows higher accuracy for the model for prediction. And finally, we have the root mean squared error, which is the square root of 1 over n, the number of data points, times the summation of the actual minus the estimated value squared. And any value between 0.2 and 0.5 reveals an good accuracy. For the ANN, we used the Liebenberg-Marquardt algorithm, and we used 3 layers. So an input, a hidden layer, and an output layer. And so we use the feed-forward neural network for this model. So feed-forward neural network means that the neuron passes through the network passes in one direction. So from the input layer to the hidden layer to the output layer, we don't have any loop. And we use the tan sigmoid activation function for training the model, which was the most convenient for neuron processing to forecast the gas density. Of course, we have other activation functions such as the sigmoid, the ReLU. But for our case, we use the tan sigmoid function, which is 2 over 1 plus e to the power minus 2x plus 1. So it will return values ranging from -1 to +1. So for the hidden layer, the amount of each neuron in the hidden layer is equal to the amount of each neuron in the input layer times the weighted average. So the molecular weight times the weighted average within the input and the hidden layer, plus the pseudo-reduced temperature times the weighted average, plus the pseudo-reduced pressure times the weighted average. And finally, we add the bias. What is the bias of the hidden layer? A bias is a constant that is added in order to help the model in a way to fit best for the given data. So it's similar to the constant in a linear equation. And finally, we have the okay, I can see, I can annotate. Okay, it seems I cannot. Okay, so the output of the hidden layer is as follows, and we need to pass the resultant value through the activation function, which is the tan sigmoid function. So we get the following as an output from the hidden layer. Now, between the hidden layer and the output layer, we do the same. So the quantity of each neuron in the hidden layer, which is this equation. So, which is this equation, this whole equation. It's the output from the hidden layer. So we multiply it by the weighted average within the hidden and the output layer, and then we add the bias of the output layer. So we get this equation. So from this ANN model, we were able to extract this equation or this correlation. So we were able to decode the black box behavior of ANN. By black box behavior, I mean that usually ANN algorithms or models, they do not reveal information regarding the system they are forecasting. So we provided a mathematical equation that can be used for future applications without the need to have any prior AI or machine learning knowledge. But of course, within the data range that we had in this study, which is between 0.004 gram per centimeter cubed and 0.753 gram per centimeter cubed. And in order to use this correlation, we should normalize the input parameters and denormalize the output parameters. Then we do normalization in order to change the numeric values of the inputs to a common scale ranging from 0 to 1. Why do we need to do that? Simply because we need to, this can result in a faster learning, and so it will speed up the learning process, and it will result in a faster convergence of the model. So this is the equation for normalization. We do y max minus y min times x minus x min over x max minus x min plus y min. So in the case of normalization, the y max and y min, they are valued as +1 and -1. The x max and x min, we get the values from this table. So for example, for the pseudo-reduced temperature, we do 1 minus -1 times x, which is the pseudo-reduced temperature, minus the minimum value, which is -3.89, over 2.68 minus -3.89 plus y min, which is -1. So we get the following equation. We do the same for the pseudo-reduced pressure and the molecular weight. And for the denormalization, the x max and x min, they are valued as +1 and -1, and we get the y max and y min from the table above. And of course, we need to convert the natural gas densities values into the original or real values. So we need to remove the log. For the ANFIS model, we use the subtractive clustering method, which is established based on a cluster radius. And from the results of the error metrics, the optimum cluster radius was 0.2, so performing the most accurate gas density predictions using the given data set. So in summary, we used the feed-forward neural network for ANN. We used the Liebenberg-Marquardt training algorithm. We used the tan sigmoid transfer function, and a single hidden layer consisting of 11 neurons. And the seed is equal to 96. What is the seed? It's a parameter that we need in order to help us reproduce the results. So each time we run the model, we are able to get results that are slightly different. So we get a result that so we have a slight difference. And for the ANFIS model, we use the subtractive clustering with 0.2 cluster radius. But here I want to go back to the ANN model. So I said that we used one hidden layer for this model, but many of you might ask, like, why you have used one hidden layer? Why not more? How many hidden layers should we usually use in an ANN model? So the answer is simply, we don't have a general rule for that. So usually the higher the number of hidden layers, the more accurate the data is, but it can generate overfitting. So the key here is intuition and experience. In our case, since the problem was not that complex, so the ultimate scenario was using one hidden layer to avoid overfitting. So if we are comparing the results of the model, so to compare the ANN and the ANFIS, so the root mean squared error for ANN was for the training data was 0.0153, lower than that of the ANFIS training data, which was 0.0287. Now the average absolute percentage error for the ANN training data was about 3.85, and for the ANFIS it was about 11.77. From the scatter plot, we can see that the coefficient of determination for the ANN training data was higher than that of the ANFIS data. So we can conclude that the ANN performed better than the ANFIS model, or the adaptive neurofuzzy inference system. And I want to highlight here that since the error of the training data and the training error and the testing error was they were similar in both ANN and the ANFIS, so we don't have overfitting here. But if the training error was higher than the testing error was higher than the training error, this means that we have overfitting. So we should take care and remove some input, some variables, so to avoid overfitting. And finally, ANN performed better than ANFIS in terms of the least squared error. We were able to develop an ANN model that allows a quick estimate of gas density within the range of 0.004 and 0.753 grams per centimeter cubed. So this research, or the added value of this research, is that we were able to decode the ANN's black box behavior by presenting a mathematical equation or a model that can be used for future applications without the need to have any AI knowledge or to know how to work with machine learning algorithms. By this, I conclude the session, and I'm ready to answer any question if there's any.
If anyone have a question, please raise your hand, and I will give you a permission to open the mic. Okay. You can open your mic now. But we have only 2 minutes.
Assalamu alaikum.
Engineer Mariam, we have a question.
Yes, is it written in the chat box? Can machine learning be used for reservoir performance prediction? Yes, of course. I mentioned earlier that we can use machine learning to improve the reservoir performance.
مهندسة مساء الخير.
Yes. مساء النور.
ممكن لو سمحت يا مهندسة أعطينا بعض steps or courses to begin or to start this career.
Yes. So as you all know now, with the online open sources, like students or even young professionals can learn or acquire skills easily. So data science and machine learning skills. I advise you to take some courses, online courses at Udemy, Coursera. We have also tons of videos on YouTube for tutorials, and recently, like from 2019, several books have been published for machine learning and Python, specifically for the petroleum industry or oil or petroleum engineering. I can suggest a book titled Machine Learning Guide for Oil and Gas using Python. It's for engineer Hasbi Yadi and Dr. Ali Rida Higagat, I think. So I suggest this book.
شكرا مهندسة مريم، شكرا.
Welcome. Okay, someone is asking if we can use machine learning for chemical engineering. Of course, we can use machine learning and AI for any field, even biology and in any field we want. So it's not limited to petroleum engineering, of course. So. Okay, I think we still have 1 minute before the meeting close. So thank you everyone for attending this webinar. I hope you all enjoyed it and learned something new. And thank you, SP Al-Azhar. I hope you all have a great evening.
Thank you, Engineer Mariam.
So should I leave the meeting, or we still have some time for questions?
You can leave. It's okay.
Okay, thank you.